In this problem, we're going to look at a pulley problem, which looks a lot like our distance problems, but has a little bit of extra stuff going on. So you have a pulley with a 50-foot rope being used to hoist some apples. The apples start on the ground 50 feet. Oh, that should actually be 25 feet. Whoops. 25 feet below the pulley. And you walk away with the rope at 1 foot per second. How fast are the apples moving when you are 10 feet away? So once again, I'm going to draw a picture to kind of sketch the general situation. And pictures are always helpful in things like this. So let's go ahead. The apples, here's the ground. Here's the pulley. The apples are they're going to be X feet from the pulley. I'm here. We're going to assume for the sake of argument that for some reason I'm pulling it with my feet, so that here's the rest of the rope. How long is this length of rope? Well, it's going to be, we have 50 feet of rope and X of it's here, so this has to be the other 50 minus X feet of rope. And this is the distance that I've traveled, we'll say, that's Y. You'll notice that X doesn't stretch all the way down, so this isn't exactly a Pythagorean theorem problem yet. But what we want to notice is that the apple started on the ground, which was 25 feet below the pulley. So even though the distance between the apples and the pulley are changing, the distance between the pulley and the ground isn't changing. And moreover, that is kind of the missing leg of my right triangle. So I can go ahead and use this to set up a related rates problem. So I'm going to start by relating X and Y using the Pythagorean theorem. But how it's going to work out is I'm going to have 25 squared plus Y squared equals 50 minus X squared, or 25 squared plus Y squared equals 2500 minus 50x, or minus 100x actually, plus x squared. So that's my general equation, and now I need to use related rates to take the derivative. So 25 squared is a constant. We'll have 2y, or sorry, I said 2y, 2y dy dt on the left-hand side. 2500 is a constant, so then my derivative will be negative 100 dx dt plus 2x times dx dt using implicit differentiation. And that will be, we can rewrite that. We can divide by 2. That will get me y dy dt equals negative 100 or negative 50 dx dt plus x dx dt. And it might help us out to factor a little bit on the right, or on the left-hand side. We'll have y dy dt equals negative, or really just x minus 50 dx dt. Okay, so we have that. Now, let's go ahead to our moment in time. What do we know? We have a pulley with 50 feet of rope. We've already used that piece of information. The apples start on the ground 25 feet below the pulley. You walk with the rope at 1 foot per second. How fast are the apples moving when you are 10 feet away? So we know that y equals dy dt, or sorry, y equals 10 because that's my distance. We know the change in y, dy dt just equals 1. X is going to be a little harder to solve for, but we do have a formula relating x and y. So x is going to equal, well, we don't know yet, but we can solve. We have that 25 squared plus y squared, 10 squared, equals 50 minus x squared. Now, you might be tempted to FOIL out this 50 minus x squared at this point, and I know I sure was, but this is actually going to be a lot easier if you just start by square rooting both sides. We know that we want to get a positive answer, so we don't really need to worry about the plus or minus all that much. So I'm going to have that square root of 25 squared plus 10 squared is going to end up being 725 if you do that in your calculator. So square root of 725 equals 50 minus x, meaning that x equals, we can add x to both sides, subtract square root of 725 to both sides. We'll get that x equals 50 minus square root of 725. How do we know that we weren't supposed to use the negative sign? Well, if I would have used the negative sign, this would have ended up being 50 plus 725, which would end up giving me something over here. I would have a negative length for this here, which would be bad. So 50 minus square root of 725 is what we want there. So we have x. Now we just want to solve for dx dt. To solve for that, we're going to use our related rates equation. We have that y times dy dt, so that's 10 times 1 equals x, which is 50 minus square root of 725, minus 50, oh, that's nice, times dx dt, we don't know what that is yet. So we'll have 10 equals, this will just end up being negative square root of 725 times dx dt. Divide both sides by negative square root of 725. And you end up with dx dt equals 10 over negative square root of 725. And that makes sense. So I did not write 725. Negative square root of 725. And that makes a little bit of sense. This length x is the distance between the apples and the pulley, and in fact that is getting smaller as time goes on. So yes, our answer kind of checks out. We should give some units to that. That's going to be feet per second. And yeah, we were able to answer that pulley problem. So like with our distance problems, it involved a right triangle. We just had to be a little bit more clever about how we set up the problem. So there you go. As a quick addendum, it is probably more important than ever that we actually write an interpretive sentence for this problem, especially because we have a negative sign in our answer. And since we were looking for speed, we're not really going to care about the negative sign. So it's probably good to just practice writing a conclusion sentence here. Saying when you are 10 feet away, the apples are moving upwards at 10 over square root of 725 feet per second. So there you go. Good to write conclusion sentences here. Here's an example of what one of those might look like. There you go.